I will begin with a word of prayer. Dear Father, we thank you for this day. Just pray that you just bless this lecture, Lord. In your name I pray. Amen. So I want to pick up talking about differentiation on norm linear spaces. I'll begin with a quote from Dudnay. And, one of the first things you might kind of be perplexed about is why aren't we talking about the derivative as a function again? And it's kind of an accident that we were able to talk about the derivative as a function. In other words, the derivative at a point just being a number. That's just a coincidence of one-dimensional calculus, because in one dimension, to each linear transformation, what's a linear transformation in one dimension? It's just multiplication by a number. So because of that, we're able to say the derivative at a point is just a number. Whereas what we learned last time is that the derivative at a point is really a linear transformation. And so this is a great quote from Dudnay. He says, in the classical teaching of calculus, the idea is immediately obscured by the accidental fact that a one-dimensional vector space, there's a one-to-one correspondence between linear forms and numbers. And therefore, the derivative at a point is defined as a number instead of a linear form. This slavish subservience to the shibboleth of numerical interpretation at any cost becomes much worse when dealing with functions of several variables. So this quote is dear to me because it's so much of what we struggle with as we first learn derivatives in general is this idea that they're not a function, that they're a linear transformation. In fact, they're the best approximation in some sense to the change in the function at that point. At various points in this lecture, you will hear Matthew and Isaac in their own fictional universe waxing eloquent. Sorry about that. And at other points, you will hear interruptions by certain Hannah. Okay, so this was our definition. Excuse me, my printer is a little bit sketchy, but basically we said if we have normal linear space V and W and some function from one to the other, then f is differentiable at a point if there's a linear mapping that satisfies this, what I call the Frechet quotient, right? And we use this notation L is dfa in such a case. In the special case that V is Rm and W is Rn, then the matrix of the differential is the derivative of f at a, which we'll denote by f prime of a, all right? But I'm reluctant to make this notation in general because generally the choice of a matrix for a linear transformation depends on the choice of basis, and so I'd rather not make such a definition in general. But you could, I suppose, if you're willing to make some conventions. Anyway, let us go on here. So I showed you, we talked about this example last time, right? This is the link between the ordinary derivative and the differential. We've learned that the relation was just this for a differentiable function. We also looked at this example that if you have a linear transformation, the differential of a linear transformation is a linear transformation itself because the Frechet quotient is just identically 0, Remember, we don't allow h equal to 0 in the limit, so there you go. Then, the next example I also talked about this briefly. The constant function has Frechet derivative, which is 0. And then the next example, which I have not looked at in detail yet, and I'll talk about right now, was this function from R2 to R3. It takes two things in, spits 3 things out. So at the moment, the way to calculate the Frechet derivative, or the differential, I should say, to this is to look at the change at x, change at xy plus h comma k. H comma k is a variable here. Xy I'm thinking of as fixed, but So what's the difference between these? Well, you plug x plus h and y plus k into this formula, and you look at the difference. You got this mess here, which simplifying and canceling leaves us with xk plus hy plus hk plus that, right? And so if you look at this, you can kind of peel off the linear piece in h and k. So that's linear in k, that's linear in h, that's quadrat, that's h times k, that's not linear in hk. This piece is linear, that's nonlinear, linear, linear. So basically the strategy here is just pick off the linear piece and say, oh, that must be the differential. Yeah, in this case it's this. You can rewrite this as a matrix like that. And so it's once I write it as a matrix, we know from linear algebra if you can write a matrix formula for it, it's automatically linear. So this L is linear, and if you look at the Fauché quotient, in other words, the difference of f minus L of hk, that works out to this here, hk comma h squared comma 0. The norm of hk is just the square root of h squared plus k squared, working with Euclidean norm in the plane. And so we just have to show that this goes to 0 as that. But we can do so with a little squeeze theorem argument, basically. Well, it's not even squeeze theorem, it's just, let's see here, I noticed that this, if we factor out absolute value of h, it gives us absolute value of h times the square root of h squared k squared, but well, that's the norm of hk. So in fact this is equal to absolute value of h times the norm of hk upstairs. That cancels with this, it just leaves you that. And of course the norm of h goes to 0 as h comma k goes to 0. So it satisfies the Fauché quotient, and in fact we find that the differential of this function from R2 to R3 is given by such at x comma y, which is kind of neat. Also, again, to recap, this kind of argument, I mean, at the moment that's all the technology we have, but we'd like to, as I showed you guys at the end of last class, we'd rather build the differential with partial derivatives. We'll get to that here today. Okay, so I think I gave a slightly different definition in class last time, but the linearization I defined to be, here's yet more notation, yay. So linearization of f at p is L sub f upper p of x. I'm going to define that to be f of p plus the differential of f at p times x minus p. You could also say that this is the affinization of f at p. So I used that on the example we just looked at so I like plug in a particular point, 1 comma minus 2. So the differential at 1 comma minus 2 is this, plugging in for x equals minus 2, x equals 1, y equals minus 2 in the previous example. And then replace, so I'm looking at x minus 1, y plus 2. That's the change in x and the change in y based at the point. So I multiply that times this matrix, and lo and behold, here's the best affine approximation to f of x, y near the point 1 comma minus 2. Okay, great. I have another example of linearization a little bit later. Let me skip ahead to that real briefly. So like another example of linearization. The one I gave you in the homework is kind of cluttered. It's got a number in it. This one's prettier. I said find the linearization of the matrix square map at the identity. So you remember last class we proved that the differential was aha. So if I plug in a equals to I, we get that dfi of h is ih plus hi, which is 2h. So the linearization is just this lif of x, f of I plus dfi x minus I. So there you have it. The best approximation to the square of a matrix near the identity matrix is just twice that matrix minus the identity. All right, so that's, when I say best approximation, that is, of course, subject to my preferences. You might consider if you're a numerical methods guy, you might find some better way of criteria for what's the best approximation. That's not a scratch I'm willing to itch here. All right, a couple more examples just from the basis of abstract derivative definition. This one here is actually subsumed by the example to follow, but here I'm looking at a complex valued function of a real variable. So an example, this would be something like, you might have f of t is e to the it, which is cosine t plus I sine t, one of my favorite examples. So here we'd have u of t would be cosine t, and v of t equals to sine of t. And basically the point of this example is to explain that to calculate the differential of such an f, you simply calculate the differential of each component function and string them together. That's basically all this example says. But here's the details. I show that if that's the derivative of u, that's the derivative of v, then if I say L of h is multiplication by the derivative times h in the complex numbers, then it's linear. And down here, the Fauché quotient you get, it ends up being basically the difference quotient for u and well, I should say the Fauché quotient for u and the Fauché quotient for v, which must both go to 0 because u and v are differentiable. So, but it's component-wise, yeah? Not especially exciting, this example, but, you know, here it is. So these are again are separately 0 because u and v are differentiable, so it follows that, in fact, the differential of f at t is u prime, the formula for it is u prime of t plus I v prime of t times h. So, like, getting back to my example, if we were to calculate the differential of, you know, e to the it at h, it would have been minus sine t plus I cosine t times h. All right, because again, well, u was, you know, cosine t, we said, and v was sine t, omitting the t dependence on the u and v, sorry. Derivative of cosine is minus sine, derivative of sine is cosine, we got the I, we got the h, and of course, it's no accident that that's also I. That's no accident that that's also I times e to the it, right? Because that's e to the it is cosine t plus I sine t, you know, so when you multiply by I. When you multiply by I, you get the minus sign, you get the plus cosine, and of course there's an h. Anyway, okay, moving on. So actually generalizing that example to a arbitrary function. So suppose you got a function that's the real input and a normed linear space output. You can write the function in terms of the sum of its component functions across the basis of v. I'm using f1 through fn for the basis of v here. And basically what I show here is just that if we define the differential to be the sum of the differentials, which each of which exists because I'm assuming that the component functions are differentiable, then I can build the differential from the linear combination of the differential for each component function. And if I do that, like, where is this stupid thing? Curses down here. It's clear that this is linear in h because, well, it is. And it also satisfies the needed difference quotient because if I, you know, take the difference up here, if I take the difference minus that, I can break it up component-wise, the difference of each component, so just factoring out the f sub I in these two terms to here. But then the thing is, this has to be 0 because we're assuming gi is differentiable. So we get each limit of each component is 0, so the total's limit is 0 by the vector limit theorem. Altogether, we learned that to calculate the differential of a vector valued function of a real variable, we can just look at the derivative component-wise and use that to make the formula like this. A related equation would be this. We can meaningfully write d sub gt, oh, really regretting putting the sub t there, I'll show you why in a second, is equal to d sub g 1, curses, dang it, 1t, no, fine, I guess I'm using f1, let me scratch that, plus plus d sub gn, the nth component function at time t, fn. In other words, the differential of g at time t is the natural linear combination of the component function differential at t. All right. Anyway. Sorry about the air conditioning noise and the other noise, but let me. Hey guys, can you go play at the castle instead, please? Thanks. I tried, guys. I tried. They're telling me no. They want to play on the swing set. Well, the castle's too hot right now. I guess let me get back to the math here, as the other conversation's hopeless. Okay, so this single example covers like real valued functions, vector valued functions of a real variable, complex valued functions of real variable, matrix valued functions of real variable, the lesson from all of these is to calculate the differential of such a thing. I can just calculate the differential of each component function, and then the net differential is simply the sum of those. All right, this is just the differential version of the comment that to, differentiate a vector valued function, we differentiate each component one at a time, yeah? Okay, enough about that. So, we worked this example last time. It's the aha one. Here it is in the notes. Let me move along. So that brings us to our next order of business, which is properties of the Fauché differential. Now, it's really, I know that the danger of me talking to you about these notes is that you won't write any of them out for yourself. So I think this section is important to get out a piece of paper and write down what I'm writing. Okay, because if you're not doing that, you're probably not getting what you need to out of this exercise here. So what I do is I introduce a new tool to help us analyze properties of the Fauché derivative. Hey guys, please, Matthew, go back to the castle, please. Now, final warning. Oh man, I made him sad. Let's see here. Now, this eta sub f is defined to be the difference in f at a plus h in a and minus the differential of f at a. All right. Now, so this I can use this to analyze differentiability. It's just a convenient notation for sort of understanding how the limiting process works for f when a few different things go on. So it's just a helpful notation to just think of this algebra collectively, all right? Technically speaking, this is kind of a bad notation because eta sub f actually has an a dependence, so maybe like a more accurate notation would be eta sub f upper a of h or something, but enough. Okay. First of all, what can we say about this eta sub f if f is differentiable at a? It relates to the Fauché quotient, right? Like the Fauché quotient is eta sub f of h divided by norm h. So we know that this goes to 0 as h goes to 0 by differentiability. But also, we might notice for h not equal to 0 and the norm of h less than 1, we have this lovely inequality, which is that 0 is less than the norm. Okay, well, it's a norm, so there you go. Less than that because we divided by something that's smaller than 1, so this makes that larger, right? This goes to 0 as h goes to 0. That, of course, goes to 0 as h goes to 0. So by squeeze theorem, the norm of the eta sub f of h goes to 0 as h goes to 0. Therefore, eta sub f of h goes to 0 as h goes to 0. And we have, that. Furthermore, we can argue that eta sub f is continuous because if we look at eta sub f of 0, it's f of a minus dfa of 0. But think about dfa of 0 is dfa is linear, right? And so 0 maps to 0 under a linear transformation. Consequently, this eta sub f is a continuous function of h. All right, which is handy because we know a few things about limits of continuous functions from our previous work in the last chapter on limits in norm linear spaces. Now, first theorem. V and W norm linear spaces, domain of f subset of v, domain of g subset of v, both differentiable at a, c a real number, then guess what? Cf plus g is differentiable at a. And the differential has the natural formula, right? So we pull the c out, and it's the sum of the differentials, just like that. This, of course, is a scalar multiplication of a map times a constant. Okay, so what I do here is to notice that eta sub f is this, eta sub g is that. Since f and g are differentiable, we have these quotients are limiting to 0. We have that the differentials of f and g are linear. Consequently, this linear combination of them is also linear because the sum of linear transformations, well, rather the linear combination of linear transformations is once more linear.
Daddy, there's something serious.
Therefore, we can calculate what? Well, bring it to me. Come here.
Matthew,
Come here.
Matthew, stop. Come to dad.
Come here, Matthew.
Oh.
Well, if he doesn't want me to touch it, then it's fine. This is very exciting, huh? Sorry for the distractions, as usual.
Okay, get it.
I had this plan of doing this last night, but then I fell asleep. I'm sorry, guys.
Want you to hold him.
All right, so He actually wants me to help him. What is the problem? I don't see anything.
It's in a different.
Oh, is it under the nail?
Yeah, there.
Oh my. Well, we'll have to start this video again here in a second, guys.